Welcome. Wherever you are watching from tonight, we are glad you are here. What we are about to examine together is small, smaller than a fingernail, smaller than the period at the end of this sentence. Under the right kind of microscope, in the right kind of light, it looks almost like a city from the air, a grid of streets and districts, of structures too regular to be natural and too intricate to be anything other than the product of extraordinary human intention. It is a microchip. Specifically, it is a KP580BM80, a Soviet-made integrated circuit produced in the late 1970s and early 1980s at the Angstrem factory in Zelenograd, a city that exists for no other reason than that the Soviet Union decided in 1962 that it needed a city dedicated entirely to microelectronics. If you were to strip back the black epoxy resin that encases this chip, dissolve it away with fuming nitric acid layer by layer until the silicon beneath is exposed, you would find something that should not, by any logic of independent parallel development, look the way it does. Because what is underneath the resin is not original. What is underneath is a copy. A hand-traced, microscopically verified, painstakingly reproduced copy of an American processor that Intel released in 1974. This is the story of how that copy was made, why it was made, what it cost the people who made it, and what it tells us about the most extraordinary industrial espionage operation in the history of the semiconductor age. The Intel 8080 was released in April 1974. It was an 8-bit microprocessor, a single integrated circuit containing 6,000 transistors arranged on a sliver of silicon, roughly 6 millimeters square. It could execute roughly 2 million instructions per second, address 64 kilobytes of memory, and be purchased for a retail price of $360. By the standards of what came before it, it was extraordinary. By the standards of what it made possible, it was the beginning of everything. The 8080 was the processor that powered the Altair 8800, the kit computer that launched the personal computing revolution, that convinced Bill Gates and Paul Allen to write a BASIC interpreter and found a company called Microsoft that persuaded a generation of engineers that a computer could be something you owned rather than something you applied to use. It was the architecture on which CP/M was built, the first widely adopted personal computer operating system. It was, in every meaningful sense, the chip that initiated the transition from computing as an institutional resource to computing as a personal one. 18 months after the 8080 appeared in American electronics catalogs, the Soviet Union had a copy. Not a licensed reproduction. Not a parallel development that happened to arrive at similar conclusions. A copy. Transistor for transistor. Metal layer for metal layer. Diffusion region for diffusion region. Derived by the systematic reverse engineering of Intel's physical silicon by a team of engineers working in a classified facility outside Moscow, under conditions that have only partially been declassified in the years since. To understand what the Soviet engineers were copying, you need to understand what the Intel 8080 actually was at the level of its silicon. 6,000 transistors sounds like a modest number in an era when modern processors contain tens of billions. In 1974, it represented the state-of-the-art in single-chip processor integration, the maximum complexity that could be reliably fabricated on a die at a 10-micron process node, tested, and shipped in commercial quantities without yield economics making the product unsellable. Those 6,000 transistors were not arranged randomly. They were organized into discrete functional regions whose layout on the die reflected, in physical space, the logical architecture of the machine. The register file, 8 general-purpose 8-bit registers, a stack pointer, and a program counter, occupied one quadrant of the die, its cells arranged in a regular array whose repetitive geometry made it the most visually distinctive region under a microscope. The arithmetic logic unit, responsible for addition, subtraction, logical operations, and the condition flags that controlled program flow occupied another region, its topology denser and less regular, the product of more complex combinational logic that did not reduce to a simple array. The instruction decode logic, the circuitry that read each opcode from memory and translated it into the sequence of internal control signals needed to execute it, was the most complex region on the die and the most difficult to reverse engineer. A dense web of transistors with no obvious repeating structure, its function distributed across a topology that required patient tracing to untangle. It was, in every respect, a complete computer on a piece of silicon the size of a thumbnail, and every transistor in it would need to be accounted for. The story of the KP580BM80 is easy to frame as a story about theft, and there is enough documented evidence of industrial espionage in the Soviet microelectronics program to justify that framing. But that framing misses something important. What the Soviet reverse engineering program represents is not merely a record of Cold War technology transfer by illegal means. It is a record of what happens when a state with genuine scientific talent, genuine engineering skill, and a genuine understanding of what is at stake technologically is systematically cut off from the commercial ecosystem that makes innovation possible. The Soviet engineers who produced the KP580BM80 were not incompetent. Several of them were among the most accomplished semiconductor engineers of their generation. What they lacked was not intelligence or dedication. What they lacked was the supply chain, the fabrication equipment, the competitive market, and the iterative culture of failure and refinement that produced the original. And so, faced with the need to field competitive computing hardware and denied the means to develop it organically, they did the only thing they had the resources to do. They took Intel's chip apart, studied it under microscopes, drew it by hand, and built it again. What resulted was a processor that was, in most functional respects, identical to its American source, and a cautionary account of how far talent alone will carry you when the system around it is broken. In 1958, Nikita Khrushchev made a decision that would shape Soviet technology for the next 30 years. Having been briefed on the significance of the integrated circuit and on the gap that was opening between American semiconductor capability and anything the Soviet Union currently possessed, he ordered the creation of a dedicated scientific city whose entire purpose would be microelectronics research and production. The city was named Zelenograd. It was built 40 kilometers northwest of Moscow, in the forest, from nothing. By the early 1960s, it had research institutes, fabrication facilities, residential blocks for the scientists and engineers who would live and work there, schools, a technical university, and the dense institutional infrastructure of a state-sponsored scientific enterprise conducted at serious scale. The Soviet leadership understood the strategic importance of semiconductors earlier, and more clearly than their public communications suggested. The problem was not comprehension. The problem was execution. Soviet semiconductor fabrication required equipment, photolithography systems, ion implantation machines, clean room infrastructure that the Soviet manufacturing base was struggling to produce domestically, and that COCOM, the Western Coordinating Committee on Export Controls, was making increasingly difficult to import. By 1970, the Soviet Union had a computing infrastructure of significant scale but increasing obsolescence. The BESM-6, the flagship Soviet mainframe of the late 1960s, was a machine of genuine technical distinction, designed by Sergei Lebedev's team at the Institute of Precision Mechanics and Computer Engineering, and capable of performance that, at its introduction, compared credibly with Western machines of the same generation. The problem was not that Soviet computer scientists lacked ability. It was that the institutional structure of Soviet computing made it almost impossible to compound that ability across successive hardware generations. Western computer development in the late 1960s and early 1970s was being driven by the commercial market. The profits from one generation of machines funded the research for the next. The competitive pressure between IBM, DEC, and the seven dwarves of the mini-computer industry created an iterative cycle of improvement that Soviet central planning had no equivalent mechanism to replicate. Each Western processor generation arrived funded by the commercial success of its predecessor and disciplined by the market pressure of its competitors. Soviet hardware generations arrived when the planning system allocated resources, which was later, and with less iterative refinement, which showed in the finished product. By 1972, the decision had been made at the highest level of Soviet industrial planning to abandon indigenous computer architecture development in favor of compatible copies of Western designs. The ES-EVM series, the Soviet IBM 360 clone, was the first large-scale expression of that policy. The KP580BM80 was its microprocessor equivalent, the same logic applied to the silicon level, producing the same result. The Coordinating Committee for Multilateral Export Controls, known as COCOM, was established in 1949 to restrict the flow of strategically significant technology to the Soviet bloc. By the early 1970s, its semiconductor controls had become a significant operational constraint on Soviet microelectronics. Photolithography equipment, the machines that expose circuit patterns onto silicon wafers, was controlled. Ion implanters were controlled. Certain categories of pure silicon feedstock were controlled. The list was long, detailed, frequently updated, and taken seriously enough that Western companies caught violating it faced substantial penalties. The effect was to create what some analysts have called a silicon curtain, a gap in fabrication capability between Soviet and Western electronics that was, by the mid-1970s, running approximately 3 to 5 years. The Soviets could design circuits of some sophistication. What they struggled to do was manufacture them at scale, to the tolerances required with the equipment available. Every generation of Western processor that moved to a finer process node, from 10 microns to 6, from 6 to 3, required fabrication equipment that Soviet domestic production could not reliably supply, and COCOM controls made increasingly difficult to acquire. The reverse engineering program was, in part, a rational response to this constraint. If you cannot build the latest chip, build a copy of the one you can manufacture. Use the Western design to compress your development time. Deploy hardware that is functionally compatible with the Western software ecosystem without having to develop the architecture from scratch. The KGB directorate responsible for acquiring Western technology was not a small operation. Line X, formerly Directorate T of the KGB's first chief directorate, employed hundreds of officers across Soviet embassies, trade delegations, and scientific exchange programs worldwide, supplemented by networks of agents recruited from Western academic institutions, technology companies, and the export industry. Its annual acquisition targets were set by GKNT, the Soviet State Committee for Science and Technology, which maintained detailed lists of the specific technologies, specifications, and hardware samples that Soviet industry needed and could not obtain through legal commercial channels. The semiconductor section of those lists was extensive and specific. It named processors, fabrication equipment models, photoresist formulations, and process documentation by their commercial designations. The acquisition tasking was not vague. It was a procurement list derived from detailed technical assessment of what Soviet industry needed to close specific identified gaps. A Western engineer reading the captured Line X acquisition lists, portions of which were published in a 1985 French government report and subsequently in American congressional testimony, would have found them technically sophisticated. They named the right targets, asked for the right documentation, and revealed an accurate understanding of what actually mattered in Western semiconductor development. The people writing those lists understood the technology. The people acquiring the items on them operated in the gray zone between legitimate technology transfer and outright theft with professional competence. The result was a supply of Western chips, equipment manuals, and process specifications flowing eastward through the 1970s and 1980s in volumes that, when they became partially known, genuinely alarmed Western intelligence services. The Angstrem Production Association was established in Zelenograd in 1963. Its name, the Angstrem, the unit of atomic scale measurement equal to 1/10,000,000th of a meter, was a statement of ambition. Angstrem was tasked with translating the research produced by Zelenograd's institutes into mass-produced integrated circuits for Soviet industry, military systems, and eventually consumer electronics. By the mid-1970s, it was the primary facility responsible for producing the Soviet copies of Western microprocessors. The KP580BM80 was its most consequential product, an 8-bit processor that would be used in Soviet personal computers, industrial controllers, military systems, and the educational machines deployed to Soviet schools and universities through the 1980s. Angstrem's engineers were not working in ignorance of what they were being asked to do. The original Intel 8080 datasheets, classified as controlled documents, circulated in the Design Bureau, obtained through the intelligence apparatus. The physical chips, acquired through front companies and black market channels that the KGB's Technology Directorate had spent years constructing, arrived for decapsulation and analysis. The process of turning a completed American chip into a manufacturable Soviet one was the responsibility of a team that understood, with complete clarity, the legal and political character of the work they were doing. They did it anyway, because they were asked to, and because the alternative was falling further behind. The first step in reverse engineering a microprocessor is to remove it from its package. The KP580BM80's American source, the Intel 8080A, comes in a ceramic dual inline package. A rectangular block approximately 40 millimeters long, sealed with a thin ceramic lid, bonded over the silicon die with glass frit. To access the die, you must first open the package without destroying what is inside. The method used in Soviet decapsulation laboratories involved fuming nitric acid. Concentrated nitric acid heated to produce vapors that attack organic and ceramic bonding materials without immediately destroying the underlying silicon or metal interconnects. The chip package was placed in a small ceramic vessel, the acid introduced, the temperature controlled carefully. Over minutes to hours, depending on the package type, the protective enclosure dissolved. What remained was the raw silicon die. A square of crystal approximately 6 millimeters across, its surface covered in the multi-layer structure of a completed integrated circuit. Diffusion regions in the silicon substrate, a polysilicon gate layer, a first metal interconnect layer of aluminium, a silicon dioxide insulation layer, and a second metal layer connecting the circuit to the bond pads at the die's edge. Under a microscope in good light, this surface is legible. The structures are large enough at the 10-micron process node Intel used for the 8080 to be photographed, measured, and drawn. The forensic analysis of a chip, the transformation of a physical artifact into a reproducible engineering drawing, begins with this exposure. Semiconductor fabrication is a war against contamination. A single dust particle landing on a silicon wafer during photolithography can ruin the die beneath it. Bridging two conductors that should be separate, blocking an exposure that should print, introducing a defect that will cause the finished transistor to leak current, switch slowly, or fail to switch at all. The Intel 8080 was fabricated in a Class 100 clean room. an environment in which the air contained fewer than 100 particles, larger than half a micron per cubic foot, maintained by HEPA filtration systems, positive pressure differentials, and the disciplined behavior of everyone who worked inside it. The Soviet clean rooms at Angstrem in the mid-1970s were attempting to meet similar specifications with a more difficult starting position. The filtration systems were Soviet-produced or acquired from Eastern European suppliers whose equipment quality varied. The building fabric, the walls, floors, and ceilings of a Soviet industrial facility was not always compatible with the contamination control requirements of semiconductor manufacturing. The garments worn by technicians, the cleaning chemicals used on equipment surfaces, the compressed gas supplies plumbed to the tools, each of these was a potential contamination source that Western manufacturers had spent a decade learning to control. Soviet process engineers were solving the same contamination problems that Western engineers had worked through in the 1960s, without access to the accumulated institutional knowledge that those Western engineers had published, discussed at conferences, and refined into standard practice. The yield figures that resulted, the proportion of good dies per wafer, were the most direct measure of how far that gap remained. With the silicon die exposed and cleaned, the second phase begins. Systematic photographic documentation of every layer of the circuit. A die is not a flat object. It is a three-dimensional structure in which the logic of the circuit is encoded across multiple stacked layers, each one deposited in sequence during fabrication, and each one contributing to the function of the finished device. To reverse engineer the circuit completely, you must document each layer separately, which means, for a chip fabricated in the 1970s, removing each layer in sequence, photographing it, and correlating the photographs to reconstruct the three-dimensional structure in two-dimensional form. The metal interconnect layers, the aluminum wiring that connects the transistors to each other and to the outside world, can be removed with dilute hydrofluoric acid or by mechanical polishing. Each removal exposes the layer beneath. A team working on the 8080 would have produced hundreds of high-resolution photographs at multiple scales. Low magnification overview images to capture the die's gross functional regions. Medium magnification images to document the routing of individual metal lines, and high magnification images to resolve the geometry of individual transistors and their gate structures. These photographs were then assembled into a composite map, a photomosaic of the die at each layer, accurate enough to allow the transistor-level circuit to be traced by hand, function by function, from the analog capture of a physical object into the engineering schematic of a design. Between the completed layout drawing and the fabricated chip lies one more translation: the production of photomasks. A photomask is a glass plate, typically 125 millimeters square for 1970s era processes, onto which the pattern of a single layer of the circuit has been reproduced at the exact dimensions required for fabrication. The chip designer's layout drawing, produced at a scale of perhaps 200:1 for the register file array, must be reduced photographically to its actual dimensions. The 6-micron lines of the Intel A280's metal layer reduced to lines whose physical width on the glass plate is 6/millionths of a meter. That reduction was achieved through a process of step and repeat photographic reduction. The layout artwork was photographed in sections, each section reduced and positioned precisely on the mask plate, the complete pattern built up from dozens of individual exposures. The accuracy required was extreme. A misalignment of a single micron between two mask layers, the gate layer and the metal layer, for instance, could shift a transistor's gate off its channel, destroying its function. The mask-making process for the KP580BM80 required a complete set of masks for each of the process layers. The active area definition, the gate oxide, the polysilicon gates, the contact cuts, the first metal, the via holes, and the second metal. Each mask had to be made at the tolerances of the Soviet fabrication process, verified against the others for registration accuracy, and reproduced in sufficient quantity to last through the production run. The quality of the mask set was one of the primary determinants of the final chip's yield. A mask with a defect reproduced that defect on every wafer that passed beneath it. The photomosaic of a 6,000 transistor chip at sufficient resolution to trace individual devices is an enormous document. At the scale required to work accurately, the transistor gates of an Intel 8080 are approximately 6 microns wide, meaning that a photograph enlarging the die to drawing scale might produce a print 2 meters across. Assembling the composite and tracing from it was a task measured in months of work by a team of engineers working concurrently on different functional sections of the die. The circuit was divided into its logical regions: the arithmetic logic unit, the register file, the instruction decoder, the control logic, the bus interface, each assigned to a small team responsible for tracing that section from photograph to schematic. The individual schematics were then integrated and verified against the Intel 8080 functional specification. This verification step was critical. A hand-traced schematic derived from photographs will contain errors. Transistors are missed, connections are ambiguous, the routing of a line between layers can be lost where a photograph is slightly out of focus or a layer removal has damaged the surface. The verification process, simulating sections of the traced circuit against the known functional behavior of the original, allowed errors to be identified and corrected before the schematic was committed to the layout design from which fabrication masks would be made. This process, from decapsulation to verified schematic, took approximately 18 months for the 8080. The result was a document, a complete circuit schematic drawn in Cyrillic annotated engineering notation that was, in legal terms, stolen intellectual property, and in technical terms, one of the most impressive acts of electronic forensics the Cold War produced. The Intel 8080 was fabricated in N-channel metal oxide semiconductor technology, NMOS. An NMOS transistor is a 3-terminal device: source, gate, and drain. The gate is a conductor, in the 8080, polysilicon, separated from the silicon channel beneath it by a thin layer of silicon dioxide, the gate oxide. When a voltage above a threshold is applied to the gate, it induces a conducting channel in the silicon between source and drain, allowing current to flow. Remove the voltage and the channel disappears. This switching behavior is the physical basis of digital logic. Gate high means conducting, means logical 1. Gate low means non-conducting, means logical 0. The critical dimensions of the transistor, the gate length, the gate width, the oxide thickness, determine its electrical characteristics, its switching speed, its threshold voltage, its leakage current, its drive capability. In Intel's 1974 process, the gate length was approximately 6 microns and the oxide thickness approximately 80 nanometers. To copy the 8080's function, the Soviet process did not need to replicate these dimensions exactly. It needed to produce transistors with compatible electrical characteristics. Slightly different geometry, differently calibrated implant doses, a marginally different oxide thickness. Any of these could produce a transistor that switched at the right logic levels and with acceptable speed, while being physically distinct from Intel's original device. This physical distinctiveness at the transistor level is exactly what the forensic comparison of decapsulated dies reveals. The same function, achieved through a slightly different physical implementation. The signature of a process that understood the principles without having access to the precise recipe. A schematic is not a chip. Between the verified circuit schematic and a manufacturable integrated circuit lies a second enormous design task, the physical layout. The layout is the translation of the schematic into the precise geometric specification, the set of mask layers from which the chip will be fabricated. Every transistor must be sized and positioned. Every wire must be routed. Every layer must be drawn to the tolerances of the available fabrication process. This is where the Soviet reverse engineering program encountered its most significant constraint, and where the KP580BM80 began to diverge in ways invisible to the functional specification but profoundly consequential to manufacturing yield and performance from its American source. Intel's 8080 was designed for Intel's fabrication process, a specific set of equipment, materials, and tolerances developed and refined at Intel's Santa Clara facility. The Soviet engineers at Angstrem were working with Soviet fabrication equipment, some of it domestically produced, some of it acquired through complex back-channel procurement from Western Europe and Japan before COCOM controls tightened. The process parameters, the minimum feature size, the oxide thickness, the dopant concentrations, were not identical to Intel's. The layout could not simply be copied photographically. It had to be redrawn to the rules of the available Soviet process. This redrawing introduced changes that accumulated across 6,000 transistors and propagated, in ways the design team could only partially predict, into the performance characteristics of the finished chip. When modern chip archaeologists, the contemporary researchers who decapsulate historical processors and photograph their die surfaces in high resolution as a form of computing history, compare a decapsulated KP580BM80 with a decapsulated Intel 8080A, the relationship between the two is immediately visible and immediately revealing. At low magnification, the functional regions of the die correspond directly. The ALU is in the same relative position. The register file occupies the same proportion of the die area. The instruction decode logic has the same general topology. These correspondences are too consistent to be coincidental and confirm that the Soviet design was derived from the Intel original rather than independently developed. At higher magnification, the differences begin to appear. The transistor geometries are slightly larger, the consequence of working to a coarser process rule set. The metal routing in some regions has been adjusted, tightened in places where the Soviet process allowed finer lines, widened in places where it did not. Some cells have been redrawn entirely, the original Intel geometry replaced with an equivalent Soviet implementation that achieves the same logical function through a different physical arrangement. These differences are consistent with a process of layout adaptation, rather than direct photographic copying, evidence that the Soviet engineers redrew the layout to their own design rules rather than simply scaling the Intel masks. The functional result was a chip that tested as compatible with the Intel 8080 instruction set. The manufacturing result was a chip that ran slightly slower, consumed slightly more power, and had a lower production yield per wafer than the device it was derived from. Close, but not identical. A copy that carries, in its transistor geometries, the fingerprint of the constraints under which it was made. A chip that tests as functionally identical to the Intel 8080 at the transistor level is not necessarily a chip that will run 8080 software correctly. Between transistor function and software compatibility lies the instruction set, the precise definition of what each of the 8080's opcodes does, under all combinations of input conditions, including the edge cases that the formal datasheet may underspecify, and that only become apparent when actual software exercises them. The Soviet verification team for the KP580BM80 faced the challenge of confirming compatibility across the full instruction set, 246 opcodes in the 8080's case, including the timing-dependent behaviors that some software relied on and the interrupt-handling characteristics that operating systems assumed. CP/M, the dominant operating system for 8080-based personal computers, had been designed around the Intel 8080's specific timing and interrupt behavior. A Soviet chip that was slightly slower, or that handled interrupt acknowledgement with a timing margin slightly different from Intel's specification, might run most CP/M software correctly, while failing on specific programs that had been written with Intel's exact timing in mind. The compatibility testing program at Zelenograd involved running a suite of test programs, some derived from Intel's own validation suite, obtained through the intelligent supply chain, some written by Soviet engineers to probe specific edge case behaviors against engineering samples of the KP5 80BM80. The failures, when they occurred, went back to the layout team for analysis. The iterative process of test, fail, diagnose, redesign, refabricate, and retest was the final stage of the reverse engineering program, and the most time-consuming one. The chip that eventually went into Soviet production had passed enough of these tests to be declared compatible. It had not passed all of them. The chips did not arrive by magic. The reverse engineering program required a steady supply of the target devices, enough samples to allow the destructive decapsulation process without exhausting the source material before the analysis was complete. Acquiring American processors in quantity under COCOM controls in the 1970s and 1980s required infrastructure, front companies in neutral countries, procurement agents with the right commercial cover, shipping routes through jurisdictions whose customs authorities were less attentive or more manageable than those of the primary Western exporters. The KGB's Technology Directorate, Line X, as it was known in Western intelligence nomenclature, was the operational arm responsible for this acquisition program. Its activities in Silicon Valley and in the electronics export markets of Western Europe have been partially documented through defector accounts and, more recently, through the declassification of some COINTELPRO and CIA files from the period. The scale was significant. A declassified French intelligence assessment from 1983 estimated that Line X was responsible for acquiring tens of thousands of individual integrated circuit samples annually, along with fabrication equipment, materials specifications, and, where possible, the design documentation that accompanied them. The individual chips on the Angstrem workbenches had usually traveled through 3 or 4 countries before arriving. They bore the physical marks of that journey, the slight corrosion that comes from improper storage, the handling marks of multiple inspections, details that Soviet engineers noted and controlled for when selecting samples for decapsulation. The Soviet microprocessor cloning program was not a secret to Western intelligence agencies. CIA assessments from the mid-1970s onward documented the Zelenograd program with reasonable accuracy, identifying the key facilities, the general methodology, and the approximate performance of the chips being produced. The more specific technical details, the exact process parameters of Soviet fabrication, the yield figures, the precise generation lag, were less well known, but the broad outline was understood. What is striking in retrospect is how little this awareness changed Western industry behavior. American semiconductor companies continued to sell chips to front companies whose ultimate destination was the Soviet Union. Not always from ignorance, but sometimes from a calculation that the commercial value of the sale outweighed the strategic cost. COCOM controls covered equipment more effectively than they covered the chips themselves, and the market for second source and industrial surplus components was large enough and opaque enough to provide effective cover for acquisition operations. The strategic community understood the problem. The commercial community had incentives that ran in a different direction, and the intelligence community focused primarily on military applications of the Soviet cloning program, paid less attention than it might have to the educational and computing infrastructure implications of a generation of Soviet engineers being trained on 8080 compatible hardware. The chips were flowing east. The awareness that they were flowing east did not translate into effective interdiction. The gap between knowing and preventing in the history of Cold War technology transfer is one of its most consistent and instructive features. The engineers who worked on the KP580BM80 and its successors were, by most available accounts, technically sophisticated people doing technically demanding work under conditions that combined genuine professional challenge with the pervasive constraint of the Soviet system. The classified nature of the work meant that they could not publish. They could not attend international conferences. They could not correspond freely with colleagues in Western semiconductor companies whose work they were, in some cases, reverse engineering in the same week it was being discussed in the open literature. Their careers were confined entirely within the Soviet semiconductor research system, a system that valued output and production targets over the peer-reviewed publication that might have given them broader professional recognition. Interviews with former Zelenograd engineers, conducted by Russian computing historians after the Soviet collapse, describe a culture that was simultaneously technically serious and institutionally constrained. People worked hard because the work was genuinely interesting. They were proud of what they had built, even when what they had built was a copy. They understood that the copies were strategically necessary. They also understood, at least privately, that the copy-based development model was a structural trap, that each generation of Soviet processors would begin its development cycle already one generation behind the Western chips it was derived from, and that the gap would not close by copying. The system that required the copy also prevented the original. In 1975, Federico Faggin had already left Intel. The man who had led the physical design of the 8080's predecessor, the 4004, and the 8080 itself, had departed to found Zlog, where he was working on what would become the Z80. At the same time, in Zelenograd, a team of Soviet engineers were working from photographs of his silicon. They did not know his name in the context of this particular chip. The attribution of individual design contributions inside a large semiconductor project is rarely public. What they knew was the circuit, its topology, its timing, its functional behavior, translated into photographic evidence spread across a drafting table in a classified facility 40 kilometers northwest of Moscow. This is one of the stranger symmetries of the Cold War semiconductor story. At almost exactly the moment when the original designer of a chip was moving on to design its successor, the engineers copying it were completing their analysis of the original. The West was building the Z80. The East was finishing the 8080 clone. The gap measured in calendar time was approximately 2 years. The gap measured in architectural generation was one full processor family. That gap would not close. As Zilog's engineers designed the Z80's extended instruction set and improved interrupt structure, Zelenograd's engineers were beginning the KP580BM80's compatibility verification. As Intel's engineers designed the 8085 and the 8086, the copy program was absorbing each new target and falling further behind the timeline it was trying to track. Production of the KP580BM80 at Angstrem began in volume around 1977. By the early 1980s, it was among the most widely deployed 8-bit processors in the Soviet bloc. Its applications covered a remarkable range. At the industrial end, it was used in programmable logic controllers, numeric control systems for machine tools, and the instrumentation systems of scientific and military equipment. In the computing infrastructure of Soviet industry, it was the processor in a family of S80 compatible industrial computers that formed the Soviet equivalent of the Western embedded controller market. At the consumer and educational end, a distinction that only partially applied in the Soviet context, where consumer electronics were largely state-distributed. It powered a generation of Soviet personal computers whose names are unfamiliar to Western computing history, but whose role in Soviet technical education was substantial. Machines like the Raduga, the Orion 128, and elements of the Electronica BK series used 8-bit processors compatible with or derived from the 8080 architecture, giving a generation of Soviet students their first encounter with programmable computation through a hardware architecture that was, under its Cyrillic labeling, American. The software that ran on these machines, the games, the educational programs, the amateur utilities distributed on cassette tape through informal networks, was written by Soviet engineers and students who were, without knowing it, writing for Intel's architecture. The KP580BM80 was, in this sense, an act of technology transfer that succeeded completely. The Soviet engineers who used it as a teaching tool were being taught, at the fundamental level of instruction set and register architecture, the mental model that Intel had built. The Electronica BK0010 was introduced in 1985 as the Soviet Union's first mass-market personal computer. Its processor was not a KP580BM80, but a K1801BM1, itself a clone of the DEC LSI-11 architecture. But the machine's place in Soviet computing culture illustrates the context into which the entire family of Soviet-cloned processors was deployed. The BK0010 retailed for 650 rubles. Expensive, roughly equivalent to 2 months of a skilled worker's salary, but accessible enough to reach private ownership in significant numbers. It connected to a domestic television set for its display, stored programs on a cassette tape player, and ran a version of Focal, a programming language, in its ROM. For Soviet children growing up in the second half of the 1980s, the BK0010 was their first encounter with programmable computation. The programs that ran on it, the games distributed on cassette through informal exchange networks, the educational software deployed through school and pioneer house computer clubs, were written by Soviet engineers and enthusiasts who had learned to program on 8080-compatible hardware and who brought that architectural understanding with them to whatever machine they worked on next. The computing culture that formed around these machines was not derivative in the way that the hardware was. The software was original, the community was real, and the technical literacy it produced was genuine. The chip beneath was a copy. The culture built on top of it was not. The KP580BM80 was functionally compatible with the Intel 8080. In a test environment, running the same software, it produced the same results. What it could not do, and this is the gap that mattered, was run at the same speed. The Intel 8080A was specified at a clock frequency of 2 MHz for the standard version and 3 for the faster variant. The KP580BM80's initial production ran reliably at under 2 MHz, with significant yield variation between wafers. The fabrication process's slightly larger feature sizes and different transistor parameters translated at the circuit level into higher parasitic capacitances and slower switching times. The chip worked. It just worked more slowly, and not all of the chips that came off the line worked even that reliably. Yield, the proportion of dies on a wafer that meet specification, is the economics of semiconductor manufacturing. A process with good yield produces many good chips per wafer at low cost per unit. A process with poor yield produces few at high cost. Soviet semiconductor yields in the 1970s and 1980s ran substantially below Western equivalents for comparable process nodes, for reasons that combined equipment quality, material purity, operator training, and the absence of the iterative process refinement that Western manufacturers had been accumulating for a decade longer. The consequence was that the KP580BM80, despite being a functional copy of the 8080, cost more per unit to produce, ran slower, and required more stringent incoming testing to identify defective parts before they were built into systems. It was a copy that embodied, in its production economics, the full cost of the system that required it. The civil and educational deployment of the KP580BM80 was the visible portion of its production run. The military applications were not visible at all, and remain only partially documented even today. 8-bit microprocessors of the 8080 class were appropriate for a wide range of embedded military applications in the late 1970s and early 1980s. Guidance system interfaces, communications encryption equipment, radar signal processing, instrumentation in aircraft and vehicle systems, and the programmable controllers that managed the sequences of industrial processes used in military manufacturing. The Soviet defense industry required processors that were domestically produced, hardware whose supply chain could not be interdicted by Western export controls and whose specifications could be verified to domestic standards rather than accepted on the basis of a commercial data sheet from a foreign manufacturer. The KP580BM80 met this requirement. It was available in versions rated for expanded temperature ranges and radiation tolerance, produced in ceramic packages that offered better environmental protection than the plastic packages used in commercial applications, and tested to military screening standards that rejected a larger proportion of production than commercial testing. The military versions of the chip cost substantially more per unit to produce, reflected the additional testing and packaging, and were allocated through the defense procurement system, rather than sold commercially. Their existence in Soviet military hardware has been confirmed by analysis of captured and decommissioned equipment, but the full extent of their deployment, the programs, the quantities, the specific systems, remains classified in Russian archives that have not been opened. By the mid-1980s, the limitations of the reverse engineering-led development model were becoming visible even within the Soviet semiconductor research system. The problem was generational timing. Each new Western processor required 18 months to 2 years to reverse engineer and adapt to Soviet process parameters. During those 18 months, the Western industry did not wait. Intel released the 8085 in 1976. The Z80, a compatible but extended design from former Intel engineers, followed the same year. The 8086, a 16-bit processor that represented a fundamental architectural step, arrived in 1978. The 286 came in 1982. Each of these required its own reverse engineering program, and each program began with a device that had already been in Western production for some time. The structural consequence was that the Soviet processor catalog was always, at best, generating behind the Western catalog it was tracking. The copies could not be sold to Western customers. They could not participate in the software ecosystem that was building around x86 compatibility. They could only be deployed internally, within a computing infrastructure that was itself becoming increasingly dependent on Western architectural decisions made years earlier. Some Soviet computer scientists understood this problem clearly and argued internally for an indigenous architecture. A Soviet processor designed from principles rather than reverse engineered from a competitor's product. The argument was serious and technically well-founded. The institutional response was limited. The pressure to produce compatible hardware was too immediate. The systems already deployed were already dependent on 8080 compatibility. The trap of copying, once entered, was difficult to exit. While the KP580BM80 program was underway, a parallel and contrasting project was developing at the Institute of Precision Mechanics and Computer Engineering in Moscow. The Elbrus computer, designed by a team led by Boris Babayan and Vsevolod Burtsev, was an indigenous Soviet supercomputer architecture, not a clone of any Western design, but an original system developed from principles. The Elbrus I was delivered in 1979, the Elbrus II in 1985. These were serious machines. The Elbrus II achieved performance competitive with the Cray 1 on certain workloads, and the architecture incorporated ideas, out-of-order execution, capability-based security, that were independently reinvented by Western computer architects a decade later. Boris Babayan and his team were proof that Soviet computer science, given the resources and the institutional space to work independently, could produce original designs of world-class quality. The contrast with the clone program is instructive. The Elbrus program had a patron. It was sponsored directly by the defense establishment, which was willing to fund original development for the highest performance military computing requirements. The KP580BM80 program had a customer, Soviet industry, which needed compatible hardware quickly and did not have the time or the institutional patience to wait for indigenous development. These two programs coexisted in Zelenograd and Moscow through the same decade, representing two different answers to the same underlying question about what Soviet computing should be. One produced original work of genuine distinction. The other produced copies that were always one generation behind. The difference was not talent. It was who was paying and what they needed. The Soviet semiconductor program did not survive the collapse of the Soviet Union intact. Angstrem and the other Zelenograd production associations continued operating into the post-Soviet period under conditions of severe economic disruption. Funding collapsed, engineers immigrated, equipment aged beyond the point at which it could be economically upgraded to remain competitive. By the mid-1990s, Angstrem was producing chips that were 2 or 3 process generations behind the leading Western foundries, competing in a market where process node advancement had become the primary competitive dimension. What survived, and what has only recently begun to receive serious attention from computing historians, is the documentary record. The technical reports, the design documentation, the internal correspondence of an extraordinary industrial effort conducted under extraordinary constraints. And what survives in the silicon itself, in the physical artifacts of the chips still found in Soviet-era equipment and collections, laboratories, and the hands of the retro-computing community, is the evidence that the forensic archaeologists have been reading for the last decade. Every decapsulated KP580BM80, every high-resolution dye photograph published by the chip archaeology community adds another data point to the picture of what was actually done in Zelenograd between 1974 and 1977. How many people, working on which sections of the circuit, under what process constraints, produced a copy of another company's product that was, by any measure, a remarkable act of applied engineering intelligence? The chips are small. The story they contain is not. The collapse of the Soviet Union between 1989 and 1991 opened, briefly, a window into the Zelenograd program that has never been fully exploited by historians. Former engineers, freed from the secrecy that had enclosed their careers, gave interviews. Internal documents were partially declassified. The computing history community in Russia, a small and dedicated group of researchers, began the work of documenting what had actually been built, when, by whom, and under what conditions. What emerged from this partial opening was a picture more nuanced than either the Western narrative of straightforward theft or the Soviet-era narrative of independent parallel development. The engineers who worked on the reverse engineering program were, in many cases, fully aware of the ethical and legal character of what they were doing. Some were uncomfortable with it. Some rationalized it as strategically necessary, which it was. Some were simply doing the job they had been assigned, in the way that engineers the world over do the jobs they are assigned, without asking whether those jobs should exist. The post-Soviet interviews also revealed the personal costs of working in a classified environment for an entire career. The publications not written, the international contacts not made, the intellectual recognition not received. Several of the engineers who had made the most significant contributions to the program were unknown outside the Soviet system, and are still largely unknown today, because the work they did was secret and the career recognition that publication normally provides was not available to them. Their chips are in collections, their names are not. There is a practice in the chip archaeology community called die photography, the systematic documentation of historical processors after decapsulation, the publication of high-resolution images of die surfaces that have not been seen since they were bonded into their packages 30 or 40 years ago. The people who do this work are hobbyists, mostly. Engineers and historians who find, in the circuit topology of a decades-old chip, a readable record of the decisions and constraints under which it was made. When you look at a high-resolution photograph of a KP580BM80 die, alongside a comparable photograph of an Intel 8080 die, you are looking at a document. You are reading a record of a specific kind of Cold War desperation. The decision, made by engineers who understood exactly what they were doing and exactly why it was necessary to take apart someone else's work and build it again under worse conditions with fewer resources and without being able to ask the people who made the original how it was done. The KP580BM80 is not celebrated. It appears in no museum of computing innovation. It does not have the cultural presence of the chips it was derived from, or the machines it powered. But it is, in the forensic record of its transistor geometries, one of the most honest documents the Cold War produced. An account, written in silicon, of what technical intelligence looks like when the system around it is too constrained to let it build something new. Strip back the resin. The evidence is all there. The field of chip archaeology, the systematic decapsulation and photography of historical integrated circuits as a form of computing history, has been one of the more unexpected developments in the retrocomputing community of the last decade. Ken Shirriff, John McMaster, and a small number of other researchers have published high-resolution die photographs of dozens of historical processors, including both the Intel 8080 and various Soviet-era chips, accompanied by analysis of their circuit topology and functional organization. This work has made it possible to conduct the forensic comparison of Soviet and Western dies that was previously limited to intelligence analysts with access to classified materials. The evidence is now public, and it is specific. At the die level, the relationship between the KP580BM80 and the Intel 8080 is unambiguous. The functional regions correspond, the circuit topology is derived, the layout has been adapted to different process rules but not redesigned from principles. This is not an accusation. It is a description of what the silicon record contains. What makes this forensic evidence interesting is not what it reveals about legality. That question was settled in its historical context, but what it reveals about the engineering process. You can read, in the differences between the two dies, the constraints under which the Soviet layout was produced. The places where the geometry has been loosened correspond to the tighter design rules that the Soviet process required. The places where the cell topology has been modified correspond to the process parameters that differed. The chip is a document. The forensic archaeologists are reading it, and what it says, when read carefully, is the story we have been telling for the last 36 minutes. Thank you for watching. If you stayed through to the end of this one, then you are the kind of person who finds history in small objects, who understands that a 6mm piece of silicon can carry inside it a complete account of the world that made it. If the story of Zelenograd and the KP580BM80 resonated with you, please consider subscribing and sharing this with anyone else who cares about the weirder, quieter corners of computing history. We genuinely love to hear from you in the comments. Did you grow up with Soviet computing hardware? Have you done chip archaeology yourself? Do you have a KP580BM80 in a drawer somewhere? Or a Soviet-era machine you'd like us to look at in a future video? Tell us what it is, Tell us where you found it, and tell us what corner of Cold War technology history you'd like us to open next. We read every comment. Some of our most interesting journeys have started from a single observation, left by someone watching from a city we hadn't thought to visit. Until next time, keep looking closely. The history worth understanding is always hidden inside something smaller than you expect, sealed under resin, waiting for the right kind of light.